Howdy, my name is Giselle Gardea and I will be talking about the memory hierarchy. The memory hierarchy technologies include random access memories, or RAMs, dynamic RAM, or SRAM. RAMs can be accessed at all locations and at the same time. Dynamic RAM is high density, low power, cheap, and slow, while SRAM's constant will last forever or until the power is turned off, and caches use SRAM for speed. As we can see here, we have the different levels of the memory hierarchy. Starting from the top, we have the registers, then the cache, which I stated above is the SRAM, the main memory, which is composed of the DRAM memory, secondary stage, which is a disk, and tertiary storage at the lower level. In the beginning, we had a simple model of memory which consisted of the main memory being in a linear array of bytes that can be accessed given a memory address and uses registers to store values. In reality, the memory model is way more complex. There are different memories that exist at different levels of the computer, and each of these levels vary in their size, and cost. Now we are going to go more in detail of the hardware side of these types of RAM memories. The RAM is packaged as a chip. The basic storage unit is a cell which has 1 byte per cell and multiple RAM chips from a memory. Static RAM or SRAM cells store bits with 6 transistor circuits, retains value indefinitely as long as it can be kept powered, and it is faster and more expensive than the DRAM memory. Dynamic RAM or DRAM has each cell store bits with capacitor and transistor, and the value is refreshed every 10 to 100 microseconds. Cache memories are small, fast SRAM base memories managed automatically in hardware. They hold access block of main memory. CPU looks first for data in L1, then in L2, then back to the main memory. This process can be displayed in this picture below. The exploit memory hierarchy is described as the availability of memory. This depends on the cost, size, and the speed. The principle of locality is described as memory references that are bunched up together. A small portion of address space is accessed at any given time. This space is in high-speed memory and not all the memory can fit, which can cause a big problem. There are two sources of locality: temporal locality and spatial locality. Temporal locality tends to access locations recently referenced. The code is within a loop, and same instructions are fetched repeatedly. Spatial locality tends to reference locations around recently referenced, are made into data arrays, are local variables in the stack, and data is allocated in big chunks. As we can see in this picture, up above we see the CPU register file that only has room for 4 byte words. The transfer unit between SPU register file and the cache is a 4 byte block. The next block is a small but fast LI cache that has room for 2 4-word blocks. The transfer unit between the cache and the main memory is 16 bytes. And lastly, the big and slow main memory has room for many 4-word blocks. Now we're going to talk about the cache. The cache, as I mentioned before, is a small and fast storage device that acts as a staging area for a subset of the data in the larger and smaller device. The information that we need to keep is the actual data, the location of the actual data, and if the data is even considered valid or not valid. The cache is organized by mapping each region of memory to a smaller region of the cache. Discard address bits by discarding the lower bits or discard higher order bits. The cache size is 4 bits. Memory address size is 8 bits. As you can see in the picture, in the first case, which is letter A, at the bottom, we have 000XXX is mapped to just the 4 zeros in the cache. In the second case, which is letter B, up above, XXX001 is mapped to be 001 in the cache. Finding data in the cache happens when part of the memory applies to the cache. The remaining is stored as a tag in the cache. The lower order bits are discarded. We need to check if 001, 0011. The cache index is the first 4 bits, which are 0001, and the tag is the lower 4 bits, which is 0011. If the tag matches, or as we say, hits, we use that data. If there's no match or we miss, we fetch data from the main memory. Direct map caches are the simplest kind of cache. This type of cache is characterized by exactly one line per set. The set selection uses the set index bits to determine the bits of interest. As we can see in this picture, we can see how the direct map cache works. Accessing direct map cache is done by line matching and word selection. By line matching, we have to value line in selected set with a matching tag. By word selection, we extract the word. Here we can see in the picture that the tag bytes in the cache line must match the tag bits in the address for it to be a match. And also, if 1 and 2 are matching, then the cache hits and the block offset selects starting byte. Because they are words, there's going to be 4 bytes in that word. Set associative caches are characterized by more than one line per set. Set selection is identical to direct map cache. Line matching and word selection must be compared by the tag in each valid line in the selective set. Fully associated caches, set selection is trivial, and accessing a line is the same as a set associative cache, but by a different scale. When updates occur, 2 different things can happen: write-through or write-back. Write-through happens right immediately. It is simple to implement and has synchronous write. It also has uniform latency on misses. Write-back happens when a block is replaced. This requires an additional dirty bit, or as we call a modified bit, and it writes asynchronously. It has a non-uniform miss latency, and if it is a clean miss, it will read from the lower level, or if it is a dirty miss, it will write to the lower level and then read it. The cache has 3 different performance metrics. The first is the miss rate. The miss rate is the fraction of the memory references where it is not found in the caches. These can be very small for LT2, and it depends on their size. The hit time is the time it takes to deliver a line in the cache to the processor, which includes time to determine whether the line is in the cache. The last is the miss penalty, which is the additional time it requires because of a miss. And that concludes this presentation. I hope you learned a lot about the memory hierarchy and realize it's not as simple as it may seem in this class. It gets a lot more complicated as we move along. Thank you.